Okay, hi. I'm going to just have a brief talk to you about Le Chatelier and his principles. Okay, so we've got, for example, A plus 2B turns to C plus D. When we're talking about Le Chatelier, everything's in the gas phase. Okay, and that's really important, particularly when we're starting to talk about things like pressure. So, the Ford's reaction is plus 250 kilojoules per mole. So, firstly, what does all of this mean? It means that, I'm just going to mute my computer. Everything here has got some form of relevance to us. So this 250 kilojoules per mole means that the Ford's reaction is endothermic. Okay, so it's endothermic. We know that because the chemicals are gaining that amount of energy, or that's how much energy it takes to bond those chemicals together. That plus is in relation to the actual chemicals themselves. Okay, it also means that the backwards reaction is going to be minus the same amount. Okay, it's the same, and that therefore means that it's opposite, so it is exothermic, the backwards reaction. Okay, now what Le Chatelier says is that we've got a system at equilibrium. Okay, so it is at dynamic equilibrium. That means that the concentration of each of those constituents doesn't change, but they are reacting constantly. We've got A plus 2B going forwards to make C plus D, and at the same time and at the same rate, we've got C plus D turning into A plus 2B. So it looks like nothing's happening, but it actually is. It's called dynamic equilibrium. Now, what Le Chatelier is interested in is what happens when we change the conditions. The conditions could be temperature, they could be pressure, it could be changing the concentration of one or several of these constituents. So let's start with, we've got some data on heats, so let's have a look at changing the temperature. So if we've got a system at equilibrium, we change one of the conditions, that system will change itself by changing the position of equilibrium in order to counteract that change. i.e., if we put heat into it, the reaction that lowers that temperature again is the one that's going to come to the fore. So we know that the Ford's reaction here is endothermic. So if we add more heat energy, we know the Ford's reaction is going to happen more. So we will get more C and D. Okay? Conversely, if we cool it down, we know that that is going to mean that the system is going to want to try and maintain the same temperature. So it's going to favour the exothermic reaction because that will heat up the reaction and try and maintain that temperature. So we'll gain more of A and B. Okay, that's fairly straightforward. When we talk about gases and pressure, we need to look at the number of moles, because each gas, we use a massive generalization here, which is that gases behave in the same way. Okay, remember the ideal gas law. That's what we're looking at now. Okay, or that's the kind of assumption that we're making here, that each of these gases is going to take up basically the same amount of space, which roughly it will do. It's not exact, but here we're not looking at exact terms, so we can make that generalization. So here we've got 1A and 2B. So there's 3 moles. That says noles. 3 moles of gas here. Okay, and here we've got 2 moles of gas. So that is going to take up 3 units of space, shall we say? That's going to take up 2. So if we increase the pressure, the way that it will relieve that pressure is by moving towards this side of the reaction.